right, y'all, today we are going to talk about how to find a limit algebraically. So on the first day, we learned how to find limits at infinity by just doing some analysis on the rates of growth of the different functions. Last time we looked at how to find the limit at a point from a table and a graph, but you won't always be given a table or a graph. Sometimes you'll just be given the equation, right, the function. And so there are many different algebraic techniques to find limits. There's going to be some limits that, like, at the end of the unit, you still won't really know how to do, that you'll learn in a later class. But what we're going to focus on are these 4 algebraic techniques to find limits. So part of the challenge here is going to be just being able to identify like what to do, right? Because I'm not going to necessarily tell you, oh, use this technique for this equation. You're going to have to look at it and say, okay, well, this kind of looks like this one type of function, and so I'm going to have to apply this technique. So we'll go through 4 different techniques, and hopefully, as we practice through these, you'll start to be able to recognize like what to look for. Now, the first technique is the easiest one. Okay? This is the one you kind of hope for. Direct substitution. Now, direct substitution will work as long as the function is continuous at that point. And what I mean by that is that at that x value, not only does the limit exist, but it equals the value of the function. Okay, so if the limit exists and it equals the value of the function, then the function is considered to be continuous at that point. We'll spend a lot more time on continuity in a few days, so we'll come back to that. But the basic idea is if you can draw the curve without picking up your pencil, then the function is considered continuous, okay? At least at that spot. So if that's true, then you can just simply plug in the x value that you're approaching, and you'll get your answer, okay? So this is what you kind of hope to happen, right? If you can plug in the number and you get a value, more than likely, that's going to be your limit. I mean, unless you have some kind of like piecewise function or some kind of jump function or something weird happening, if you can just plug in the value, then that will be the value of your limit. So let's go through a couple of these. Like if I want to find the limit as x approaches 5 for this rational function, x plus 7 over x squared minus 2, well, I'm just going to try to plug in 5 and see what happens. So this will be 5 plus 7 over 5 squared minus 2. So 12 over 25 minus 2 would be 23, and that's the value of your limit. Pretty straightforward. Hopefully the arithmetic's not too bad. Most of these you really shouldn't need a calculator for. I'm not going to like give you something like 23 to the 4th power or 17 divided by 6 and give me the decimal equivalent or anything like that. You can just leave it as a fraction. In fact, if these are free response questions, you actually don't need to simplify at all. So if this were a free response question on the AP test, you could actually just be done right here and then box that as your answer. Okay. Now, I want you to be able to simplify because, like, especially on the multiple choice section, they're always going to be simplified. So you want to kind of just get in the habit of doing that. But as we start to actually prepare for the AP test, it's going to be a hard habit to break, but you actually don't want to simplify anything. You don't want to open up yourself to a mistake. All right, so B. Let's try to plug in pi, see what happens. So we got cosine of pi over pi. Now, what's the cosine of pi? You happen to remember that? Okay, yeah, good, -1. Yeah, -1 over pi. And that's your limit. So just as a little reminder about, sine and cosine, you can think about the unit circle. That thing's never going to go away, by the way. And pi radians is equivalent to 180 degrees. That's going to put you right here. The coordinate is -1, 0. And when I want the cosine of the angle measure, I'm really looking at that x coordinate, which is why that's -1. Okay, there's a lot more to the why is that, but that's just kind of the 30-second explanation there. All right. Letter C. Want the limit as x approaches 3. So you know what to do. 3 squared plus 3 times 3. 9 plus 9 is 18. So these are the easy ones, right? And this should be kind of your number one strategy. Is just try to plug in and see what happens. You know, hope for the best. But more often than not, what's going to happen is your function is going to be undefined. And so you can't use direct substitution. So like for instance, if I were to try to substitute 5 into this rational function, the denominator would become 5 squared is 25. 5 times 5 is 25. The function is undefined there. But just because a function is undefined doesn't mean we don't have a limit. We do have some cases where we have a removable discontinuity or a hole to where we saw like, hey, if all you have is a hole there, you still could have a limit, right? If you have a vertical asymptote, you don't. So if the x value is going to just make the denominator 0, there's not going to be a limit there. It does not exist. Still got to kind of figure out if it's positive or negative infinity, but there's not going to be an actual limit. But if it is just a hole, then there will be a limit. So to find what that limit is, we need to factor and then cancel out the like factors that are causing the hole, and then we can use direct substitution. So let me show you algebraically how this will play out. So this is going to equal the limit as x approaches 5. You really need to make sure you're writing that. It's kind of annoying to write that on the step, on almost every step. But if I leave it out, then I'm going to be making an incorrect statement. What I mean by that is like the limit of this doesn't just equal the function, right? The limit is a specific value. So anyway, the limit as x approaches 5 of, now how would the numerator factor out? It's a difference of 2 squares. Yeah, x plus 5, x minus 5. And then the denominator is not a difference of 2 squares, but it does have a GCF. So we can factor out an x, leaving me with x minus 5. So you can see we've got those like factors. Normally, you're not allowed to just cancel those out, because if you cancel them out, you're removing the hole. That's why it's called a removable discontinuity. The function would not be equivalent. In other words, like x plus 5 over x, if I look at the graph of that function versus the graph of this function, they will look identical, except this one has a hole at 5, and this one doesn't. So this one is the same function as this, but the hole is filled in, which is why we can go ahead and use direct substitution now, because that we just filled in the hole. We know the y value of that hole is going to be the value of the limit. So now that we've filled in the hole, we can just go ahead and plug it in. So yeah, these x minus 5s are going to reduce to 1. So this will equal the limit as x approaches 5 of x plus 5 over x. So in other words, the functions themselves aren't equal, but the limits are. This is another reason why it's important to put equals and then put that little limit notation in there. So that's what allows you to cancel those out. Now we can use direct substitution. Yeah, now there's no issue plugging in 5. So now we've got 5 plus 5 over 5, which is 10 divided by 5, which is 2. By the way, this is kind of how you find the coordinates of the hole, like back in Algebra 2, or maybe you did this in pre-calculus. And, you might have said, oh, find the coordinates of the hole. Well, we already knew what the x one was. It was 5. But to find the y coordinates, you do this whole factor and cancel thing, and then just plug it in to get the y coordinate. So that's kind of what we're doing here. All right, so let's try the next one. Now, how do you know that you're supposed to factor because it's not going to say, oh, factor and cancel. It's just going to give you the function. Really, like if you see something that is factorable, go ahead and factor it. More likely than not, that's what's going to happen, especially if you're getting an x value that makes the denominator 0. Now, if the x value doesn't make the numerator 0, then you actually don't have to worry about that because it's going to just be undefined anyway. But notice how like 1 here is going to make both the numerator and the denominator equal 0. So that's how you know you have that hole. All right, so we need to go ahead and factor. Looks like the denominator. And for the most part, the factoring shouldn't be too bad. There are going to be a couple of you might encounter from time to time a quadratic that has a leading coefficient that's not 1. But even on those, there's usually some kind of hint as far as like what the factors are. We'll get to that when we do. But like this one, the leading coefficient is just 1. So all we need to do is come up with 2 values that multiply to give me -8 and add up to 7. So yeah, what are my factors here? -1 and -7. So -1 and -7. So that would multiply to be positive. So you got the sum and product backwards. Yeah. Yeah, 8 and -1 will work. So +8 -1. Now, we have like a little bit of another problem here though, right? It's not the same factor. 1 minus x is not the same as x minus 1. So at least immediately, I can't just cancel those out. I can't reduce that to 1. But what I can do, and this is going to happen from time to time where it's like almost the same factor, but the signs are all reversed, is just to factor out, as though it's a GCF, a -1 from the top, from the numerator. If I factor out a -1, that is going to flip both of those signs. And so that's how you're going to deal with a situation like that. Now I can go ahead and reduce those to 1. Reduce those to 1. Zoom in here a little bit. So this will equal the limit as x approaches 1 of -1 over x plus 8. And now I don't have any issue plugging in 1. And that's kind of what you're going to do with all these is you got to manipulate the function so that you don't have a problem just doing the direct substitution. All right, so I plug in 1 and I get -1 over 9, and that's your limit. Any questions about factoring and canceling? I know factoring is like, that's a skill that kind of comes and goes. Yeah.
On the AP test, do we have to write the whole entire equation of what the limit approaches?
Like, are you saying like, do you have to write this thing?
Yes. As your final answer?
Like down here?
Yeah.
No. So what you have to do is write logically. If you're going to write an equal sign, you have to make sure the two like sides of that equal sign are equivalent. Okay? So this is equivalent to this. But if I didn't write limit, now the left-hand side is not equivalent to the right-hand side because this is just a function, doesn't have a specific value. This has a specific value. So you're saying like, what you're saying without this is that -1/9 equals the whole function. But this is not a constant function. So that would not be true, and they'll dock you for that. But the reason why I didn't write it here is because from this step to this step, I'm actually evaluating the limit. So I'm saying the limit of this function is -1/9. Does that make sense? Yeah. Like, so in this case, the left-hand side does equal the right-hand side. And so ultimately you're saying this equals this. Yeah. So you got to be a little careful there. I'm not going to be like totally strict about that up front, but like as we get closer to the test, it's like kind of like when you're writing an essay, you got to make sure your commas are in the right place. Yeah. Make sure you got your period, So yeah, does that okay. Yeah, good. Okay. Good question. And it's easy to get sloppy. Like, if you ever did any like trig proofs, like this is a good, kind of analogy is like, writing like all the sines and cosines, it can be annoying to write sine of x like 100 times. And so sometimes you just get sloppy and write sine, cosine. But really, you have, like, in order to be logically equivalent, you need those parentheses in the x. So it's kind of that same idea of like grammatically, in math grammar, like you really do need it there to make it make sense. Yeah. Okay, here's one that looks more complicated than it really is. After you do a couple of these, you'll start to see the pattern, and it won't be as hard as it is the first couple of times. But we can see here that, like, if I try to plug in 13, the denominator is going to be 0. That's not going to give me anything, right? If I plug in 13 to the numerator, I get 0. So I know there's a hole there somewhere, because it's that x value is making both the numerator and the denominator 0. I'm not going to be able to do any factoring here. I don't have a quadratic to work with or any GCFs or anything like that. So I'm going to have to do something different. I'm going to have to rationalize the radical using a conjugate. Okay, so conjugates. Conjugates are like a plus b and a minus b. Those are conjugates. If you're talking about imaginary numbers, a plus I and a minus bi. If you're talking about like these kind of radicals, it would be like root x plus a and root x minus a. And what we're going to do is we are going to multiply both the numerator and the denominator by the conjugate of the side that has the radical. Okay, and hopefully after we kind of go through it, you'll see why we want to do that. So, so let's multiply this by the square root of x plus 3, that's like my root, plus 4, so the conjugate's plus 4 instead of minus 4, over that same thing. Now, it looks like the algebra is going to get kind of out of hand here, because really we've got to FOIL this out, right? Like if you're really trying to take it step by step. So I've got to multiply like this whole radical by this one. I've got to multiply it by the plus 4. I've got to do all this, right? And you can kind of see, oh, that doesn't look too nice. But if we look at it a little closer, we just kind of compartmentalize each of the steps. If I multiply like square root of x times the square root of x, what does that equal? X, right? Equals x. It just equals whatever's underneath the square root. So if I multiply the square root of x plus 3 times the square root of x plus 3, that's just going to equal x plus 3, right? If I multiply this by this, I get x plus 3. Okay? The other two cancel out. That's why we're doing the conjugate. It's because we want the next two terms to cancel each other out. We're getting rid of the square root by doing this. So like I've got this square root times 4, and then the next term will be the same square root times negative 4. So I've got 4 times the root minus 4 times the root. Those two will sum to 0. So they go away. Right? And then the next term is going to be negative 4 times 4, which would be minus 16. So that numerator cleans up pretty nicely. The denominator doesn't clean up so nicely, and what I highly recommend is you just don't clean it up. Don't multiply it. Leave the factors separate. It is intended to be that way, okay? And you'll see why momentarily, or maybe you already see why. So in the denominator, I'll have this x minus 13 times the square root of x plus 3 plus 4. How does the numerator simplify? What's 3 minus 16? Negative 13. Aha. This is what we want to happen. Do you see? Or I guess I do need parentheses there. See what's going to happen here? Now we can reduce, well, it's going to be 1, right, on the numerator. Oh, you may be a step ahead of me already. Yeah, or I don't know. Let's see. So yeah, now we've got that x minus 13 as a factor on both the numerator and the denominator. So we can reduce that to 1. That's what's causing the hole, by the way, is the fact that you have that same factor on top and bottom. The 13 is making both the numerator and the denominator 0. So if we remove the hole, remove the removable discontinuity, that's why it's called that, by the way, yeah, that just becomes 1. So this should have some equal signs in here. So this equals the limit as x approaches 13 of 1 over the square root of x plus 3 plus 4. And now that we've removed the removable discontinuity, or the hole, we could just use direct substitution and just plug in 13. And so this will equal the limit as x approaches 13, or actually we don't even need that. We could just go ahead and plug it in at this point. So 1 over the square root of 13 plus 3 plus 4. As soon as you do that direct substitution in, that's where you stop writing limits, because you're now evaluating the limit. All right, 13, that plus 4 should be in the denominator. My bad. So yeah, 13 plus 3 is 16. Square root of 16 is 4. 4 plus 4 is 8. So this equals 1/8. Yeah. So taking the square root only reports back the positive number. So square root function can only have one output. And it's always what we call the principal square root, which is the positive version. The reason why plus or minus came up before is because we were taking the square root of x squared, which equals the absolute value of x. Yeah. So that's why, like, when you're solving and you have like something like x squared equals 9, you take the square root of both sides, you might have just been told, oh yeah, it's just like x equals plus or minus 3. Just slap on the plus minus. But really, the reason why you're doing that is because when you take the square root of both sides, you take the square root of x squared, you get absolute value of x. You usually don't write that, but that's where the plus or minus is coming from. Yeah. And when we have a limit, you can only have one value. Yeah, you'll never have a limit that takes on multiple values. All right, let's try the next one. All right, so what are we going to multiply both the numerator and the denominator by here? Square root of x plus 3. Yeah, you want to multiply by the conjugate. Yeah, there we go. Okay, so when you do this, only multiply the conjugates out so that you can get the radicals to cancel out. The other side, don't bother multiplying it out. Just leave it the way it is, because we're going to want one of those factors to cancel out anyway. So in this case, leave the numerator as is, just x minus 9. This is like what's causing the problem, right? This x minus 9, or causing the removable discontinuity, times the square root of x plus 3, over, now let's multiply this out. Square root of x times square root of x is just x. Square root of x times 3 would be 3 root x. But then you have a minus 3 root x. Those cancel out, and that will happen every time we get those two middle terms to sum to 0. And then 3 times negative 3 is going to be negative 9. And that's kind of what you're hoping is going to happen, because now we've got those factors that can reduce to 1. And these two reduce to 1. So the limit as x approaches 9 of, well, in this case, just root x plus 3, we don't even have a fraction here, so there really should be no problem plugging in 9. So we get the square root of 9 plus 3, which you just get 3 plus 3 is 6. We're doing great on time. Okay, yeah. This didn't take as long as I thought it would. Any questions so far? Yeah, great. Fractions. Everyone's favorite. Yeah, everyone loves fractions. You got to know your fraction rules. You have to know how to add fractions, how to multiply fractions, how to subtract fractions, how to find a common denominator in order to add fractions, and all that kind of good stuff. So if you have a bunch of fractions in your limit and you can't use direct substitution because it's causing a divide by 0 error, well, we're going to go ahead and try to combine these fractions. Try to simplify this so that instead of having multiple fractions inside the expression, we just have a single fraction. So that's kind of our goal here with these fraction problems. So now this one already has a common denominator, right? The common denominator here is x plus 2. So I can go ahead and add the numerators and leave the denominator as just x plus 2. And then once you simplify it to be just a single fraction, most of the time what's going to happen is it's just going to turn into a factor and cancel problem, where you just have to factor what you have, remove the removable discontinuity, and then use some direct substitution. The numerator here, we can factor out an x, and we get that x plus 2 that we're looking for. So what's kind of interesting is that we reduce this, and then the function just becomes x, right? So what this means is that this whole expression is really just the parent linear function, y equals x, with a hole at -2. So like if you were to graph it, it would just look like this, but like at -2 you have a hole. Yeah. Looks way more complicated than that when you look at the equation. All right, so you don't really need to know that for now, but okay, so we can reduce this to 1. So now we have the limit as x approaches -2 of x over 1, which is just x. And so direct substitution, there's not even any arithmetic to do. Just plug in that -2 and you're done. Now let's say you did not have a common denominator. If you don't have a common denominator, you have to get a common denominator by multiplying one or more of the fractions by some special form of 1 to force the denominators to be the same. So if I look at this one, the right fraction is 2 over x squared plus 1. That x squared, I'm sorry, minus 1. The x squared minus 1 is a difference of 2 squares, right? It's x minus 1 times x plus 1. So it already has the factor of x minus 1. It's already got this. To find a common denominator then, all I need to do here is multiply both the numerator and the denominator by x plus 1. And when I do that, the denominator will become x squared minus 1, and then I can go through and kind of go through the motions of getting the limit. So yeah, I want to multiply. Well, I guess I'll just go ahead and say I'll write it as a separate step. I'm going to multiply this by x plus 1 over x plus 1. So this will be x plus 1 over x plus 1 times x minus 1. And maybe I'll just go ahead and leave this in factored form. don't know if there's really going to be an advantage to leaving it in standard form. Now I've got a common denominator, so I can combine these fractions. So we get x plus 1 minus 2 over x plus 1 times x minus 1. One minus 2 is negative 1. So we get that factor that we need to cancel. Those are going to reduce to 1. Now we've got the limit as x approaches 1 of 1 over x plus 1. And so now we don't have any issues doing direct substitution. Just go ahead and plug that number in. So yeah, 1 over 1 plus 1 is 1/2. Any questions about any of these algebraic techniques? Yeah.
So these are used only when there's going to be a hole in the graph, but even when you substitute. Like if there's not going to be a hole in the graph, the first thing that you should do is
Substitute.
Okay.
Yeah, that should be like your number one, like just try it and like see if you get a number, then you're usually pretty
the only
good.
thing that prevents it is the hole.
Or a vertical asymptote,
Okay.
right? But if, in the case of the vertical asymptote, then you won't have to do any of this because the function will go to either positive or negative infinity. So there won't be a limit. It does not exist. And that'll happen if that number is making the denominator 0, but not the numerator. Yeah, so if you get something like 5 over 0, then it's likely an asymptote. All right. Yeah, any other questions? Algebra's getting a little intense here, I know. Yeah, that's, it's pretty common for calculus students to struggle the most with the algebra. Like the calculus concepts themselves are usually not as difficult to get your head around. It's the algebra and just like the attention to detail that gets you. So it just takes practice. Okay. Now, if you're not really sure what's going on, especially when you have piecewise functions, sometimes it's good to just sketch a graph out. And it doesn't have to be super detailed, but it can definitely help you to understand what the limit is. So we've got this function, 3x minus 5, as when x is less than 2, and x squared when x is greater than or equal to 2. So now here's 2. So I'm just going to draw a little vertical line here, just kind of highlight that. That is going to be kind of where I'm switching from that first function to the second function. So the first function is 3x minus 5. That's going to have a y-intercept of negative 5. So 1, 5. Okay, so do this one in red, this piece. And the slope is 3. So 1, 2, 3 over 1, 1, 2, 3 over 1, and then we're here. And I'm going to do an open circle because it says x is strictly less than 2. So I've got this segment on the left. And then as soon as I hit 2, and including 2, I'm going to start graphing x squared. Well, what's 2 squared? 4. Yeah, so 1, 2, 3, 4. Got a point here. And it's just the parent quadratic graph. Hopefully you're familiar with that. It's just a parabola. Yeah, it's got points like 0, 0, 1, 1, 2, 4, 3, 9. And so basically, like you're seeing like this part of the graph. Okay, now once we have the picture, I think finding the limits is a lot easier now. What's f of 2? Is there any more of this? Oh, you know what? Is that for the next quiz? Oh, I guess not. Oh, yeah, that's for this one. Okay. So f of 2 is, I'll write it over here. Wait, how much? Yeah. So yeah, f of 2 is 4. By the way, you don't necessarily need the graph. Like, if you can kind of picture it in your head, if you can, and even if you can't, if you're just trying to evaluate f of 2, you can just plug it into the equation, right? 2 is, I guess I did them both in red, so that's not helpful. 2 is greater than or equal to 2. So this function's value is going to come from this second piece. And you could just do 2 squared. What's the value of the limit as x approaches 2 from the left? So from the left would be like from this direction. So it's 1. Yeah, the limit, oh, you know what? This one actually asks for to the right first. That's okay. So to the left is 1. The limit as x approaches 2 from the right, 2 is 4. Now, when you're trying to evaluate these one-sided limits, if you don't want to bother with the graph, if you understand that these two are both continuous functions, like just in and of themselves, then you can use direct substitution. You just need to know which number to substitute it into. So like for the left-hand limit, I would substitute in 2 to the left part of the graph, 3 times 2 minus 5. The right-hand limit, I could just substitute into the right-hand part. Right? 2 squared is 4. What is the limit overall? Yeah, it does not exist. The limit as x approaches 2 as a whole does not exist. And that's due to the left and right-hand limits not being equal. What's the limit as x approaches 5? Yeah, and you can get that either, we don't have that on the graph, I didn't label it, but we know that x equals 5 is like on this piece, so we can just use direct substitution in that piece. And 5 squared is 25.
And as long as we know it's continuous and limits, right?
Right, which all polynomial functions are. Yeah. And we'll do a deeper dive into continuity in a few days, but so yeah, the limit as x approaches 5 is 25. Now let's say that discontinuity was not a whole, kind of like what you were asking about earlier. You know, what else? You know, we had. Let's say we have a vertical asymptote instead. Or actually, no, this one's not going to have a vertical asymptote where I want it to be. Oh, that's okay. Well, we'll go over that maybe next time. So yeah, here we've got a rational function in the numerator and a constant in the denominator. Let's start with f of 1 and try to do it without the graph.
6.
Yeah, it's just 6, right? We're going to look at the domain restrictions for each piece and just pick the one that 1 belongs to. 1 belongs to 1, yeah? So our output's just 6. But if I want the limit as x approaches 1 of this function, now I have to look like on either side, meaning I've got to now be looking at the other function and find the limit where that goes to 1, or where x goes to 1 for the top piece. Okay, so this will equal the limit as x approaches 1 of x squared minus 3x plus 2 over x minus 1. What's happening here is we're basically forcing a hole into this equation, there looks like there may already be a hole there, and we're filling it in with a 6. So there's going to be a point. We'll see. I don't know what the answer is here yet, but I'm suspecting that the 6 is not going to be the point that like fills the hole. It'll just be like somewhere disconnected from it. But yeah, let's do the factoring and see what happens here. So the limit as x approaches 1, the numerator factors as x minus 2 and x minus 1. And again, if you're kind of struggling with the factoring, know that these are going to be set up so that we can get something to cancel. So like the clue as far as like, well, one of the factors is probably going to be x minus 1. Yeah, and then that can kind of help you figure out what the other factor is. So now the x minus 1s will reduce. So we have the limit as x approaches 1 of just x minus 2. And now we can use direct substitution. So 1 minus 2 is negative 1. So this is going to take some practice. Yeah, I mean, you really got to be on your game algebraically to be successful with this. So that's it for today.